Welcome to my Physics 2212 Lab 3, where we will be exploring magnetic dipoles and the Biot's of Art law, as well as magnetic fields and how they relate to distance. For this lab, we will see the relationship between the magnetic field and the distance from a magnetic dipole. We will do this through the application of the Biot's of Art law. Following the experiment, we will see that the magnetic dipole moment has a magnitude of 1.87 joules per Tesla, and that the magnetic field was proportional to the distance to the power of negative 3.28. This result is different from the known theoretical result of negative 3. For this experiment, we will be using a magnetometer app on our phones to determine the magnetic field of points on the axis of the magnetic dipole. Before doing this, though, we need to account for the magnetic field of the Earth by rotating the phone until the x component is 0. Then, we need to find the magnetometer chip in the phone by moving the phone to the maximal x component and minimal y component with the phone in both orientations. The magnetometer chip would then be where the phone is marked with an x in the diagram. Following this, we can do the experiment to find the magnetic field at different distances from the magnet on axis. The experiment applies the Biot's of Art law, where we will use the formula where the magnitude of the magnetic field of the bar magnet is some constant k times the distance to the power of some value n. We will then find the value of n experimentally as well as k. We then found the experimental data shown in the first two columns of the table. We then took the natural log of both values so we may apply the equation shown and find an experimental value for k and n. Plotting the natural log of distance against the natural log of the magnetic field gives us the plot shown. If we simplify the model to a linear system and compare the endpoints, we get that n is equal to negative 3.287 and that k is equal to e to the power of negative 14.8, which gives us that the magnitude of the dipole moment is 1.87 joules per Tesla. This result for n is slightly different from the known theoretical value of n is equal to negative 3 that we know for magnetic dipoles. This difference could have come from a source of error in measurement or error from the magnetometer app. We then repeat the experiment at a 45-degree angle away from the magnet. We did this by first finding the distance on the x-axis the phone must be for the magnetometer app to read 100 microteslas, then moving it in the y direction the same distance. We then measured the x, y, and z components to get the net magnetic field of 1.79 times 10 to the power of negative 4 Tesla as the average of 3 trials. We then created a model in GlowScript of the off-axis angle model to compare a theoretical result to the experimental result. The code is shown calculating the magnetic field according to the formula for the magnetic field of a bar magnet not on an axis through the poles. We then get that the magnitude of the net magnetic field is equal to 2 times 10 to the power of negative 5, which is significantly smaller than the experimental result found of 1.76 times 10 to the power of negative 4. The value of n that we calculated caused the result to vary more significantly than the theoretical model would have. There are some hypothetical questions that also need to be addressed. First, if we had not accounted for the magnetic north, then our results would be less accurate as we would have an unaccounted for magnetic field acting. Next, if we stuck two magnets together, our magnetic dipole moment would be doubled, as the length of the magnet would have doubled. Thank you for watching.